This is Module 26, Surface Area Prisms and of Cylinders. We're going to go through this. This is where we're getting into a third dimension and actually figuring out and calculating certain things, namely surface area, prisms, and cylinders. There are formulas that are associated with these two figures that you have to know, but first thing we have to do is basically define what a prism is. A prism is a polyhedron, remember that was in the previous module, with two congruent faces, and we call those bases, that lie in parallel planes. So if you think about it, the octagonal prism, the reason it's octagonal is because you have the top and you have the bottom are the exact same figure. They're octagons, so we say an octagonal prism. The lateral faces of a prism are parallelograms formed by connecting the corresponding vertices of the bases. So parallelograms, in this particular case, the parallelograms, they're basically rectangles. So you have to think about it. You have a rectangle for each one of these. Rectangle, rectangle, rectangle. For each one of the lateral faces. Lateral means up and down. So the lateral edges, those are these guys right here. The actual edges are the segments connecting the corresponding vertices of the bases. So you have basically the vertex here and the vertex here. Those are connected by your lateral edge. You have a vertex here and you have a vertex here. Those are connected by the lateral edge. Okay, so we have in the right, I'm going to be referring to a pentagonal prism. We have the surface area. The surface area of a polyhedron is the sum of the areas of its faces. So the lateral area, I might ask you to find as well, that would just be think of it as the up and down area. It's the lateral areas of the polyhedron is the sum of the areas of its lateral faces. So if I have surface area, you have to think of the top, the bottom, and then all of the lateral faces. So we have a lateral face here, 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 and we have a lateral face here. And this actually helps to have a prism to actually physically look at a prism. It can be a little bit difficult to kind of visualize this on a two-dimensional surface, which I have here. So think of it, again, you have the top, you have the bottom, and then you have all the sides that are basically making up the lateral faces. And if you calculate the areas of those with the certain formulas that we have from previous modules, you will be able to figure out the total lateral area. And if you add the top and the bottom, you'll figure out the total surface area. So, talking about surface area, one thing that is actually a really good analogy visual is something called a net. And a net is a two-dimensional representation of the faces of a polyhedron. So if I basically took a polyhedron and put it in a two-dimensional surface, we have our lateral face here, 1, 2, 3, 4 lateral faces, and then we have a base here. So if I were to fold all of these up, I would make my polyhedron right here, which would be a square pyramid, because I have a square for the base. This is my square base, and you can see that by the actual net here. And then all the other parts are triangles that come to a single point here. So this is one version of a net. If you wanted to look on either Google or Yahoo, you could look up many different geometric nets, and it would give you things like for cubes, for many different pyramids, for many different prisms as well. Okay, so we have right prisms. In a right prism, each lateral edge is perpendicular to both bases. So that means perpendicular, that means a right angle is created with the actual top or first face or top face and the lateral edge here. So this is the lateral edge, which I'm talking about, this rectangle here. So that means a right angle is created by the intersection of those two. If you have something that's kind of slanted on its side, we call that an oblique prism. And an oblique prism is a prism that with lateral edges that are not perpendicular. So if you notice, this angle right here that's created is not a right angle with the top and with the actual rectangle here. So, many different forms of oblique prisms and right prisms that we'll be dealing with. Okay, so now we're going to get into the actual calculation of things. Example 1 says find the surface area of a rectangular prism. So it tells us it's a rectangular prism, which means I'm going to have two rectangles, one on the bottom, one on the top, and it tells me the height is 2 centimeters, the length 5 centimeters, and the width is 6 centimeters. Now, visualizing this, what I would suggest doing is drawing an actual prism. To draw an actual prism, you would start off, since it's a rectangle, start off with a rectangle here, start off with another rectangle here, and just connect those using lines. And I'm not the greatest of artists, but I can draw something that resembles a rectangular prism. So I'm going to use the computer format to actually create something that's a little bit easier to look at. So the prism here with the length of 2 for the height, length of 5 for this for the length, and then the width is going to be 6 centimeters, which means that I have, it's saying find the surface area. I have to literally figure out every area of rectangle and use area of a rectangle, which I told you was little b times little h, for the different rectangles that are formed within this figure. So the cool thing is how you can split it up. You don't have to think of it like this complicated net here. Some people like to visualize that, but others actually like this guy right here, because when I tell them you have the front and you have the back, those are the same. You have the right side, you have the left side, those are the same. You have the top, you have the bottom, those are the same. So literally you have to do 3 calculations and then multiply each one by 2. So if I do that, the left and right faces are 6 by 2, and we multiply those, we get 12 centimeters. So 6 by 2, which means you have a 6 length by 2 width. That's the first one. The front and back faces, those are 5 by 2. So if you look, you have 5 by 2. So we have a 5 length here by 2 length here, and that goes exactly the same for the front and the back as well. So you have 10 centimeters for each one of those faces. Then you have the top and the bottom. So the top and the bottom goes for length here, width here, depending on how you look at it, 5 by 6, or in this case 6 by 5. You multiply those, you get 30. So what do you have to do? You have to add the areas of all the faces to find the surface area, which means you have to multiply each one of these values by 2. So you can multiply this by 2, by 2, by 2, and you get this equation here. When you add these up, it's surface area, so you have to make sure that you put centimeters squared. That's the key with this. So units are going to be very important in this, because we're going to be talking about surface area strictly. Okay, in this one it says find the surface area of a right prism. This is probably one of the harder ones that you're going to get. So it says find the surface area, it's right, and it's a pentagonal prism, which means you have a pentagon on the top and the bottom. And the thing that I'll tell you is that you're always going to have, if you notice the labeling here, and I won't give you anything different than this, it's always going to be a regular polygon if you have like a rectangular prism or a octagonal prism or something like that. It's always going to be regular when it gets into the higher level ones like pentagon, hexagon, heptagon, those type of things, because you have formulas that can actually find out areas of those. So those are always going to be regular. So in this case we know it's regular because based off of the labeling. So what do we have to do? We have to find out, first of all, find the perimeter and the area of the base of the prism. So the reason you have to find the perimeter is because the perimeter is involved in area. So what I'm going to do, this is when you had to find your central angle, divide it into 2, and find out the different parts of the triangle. So what I have my radius here. This is this triangle blown up here. Okay, I have a radius of 6. I have a radius of 6. The side length I know is 7.05 here. So I can transfer that because it's congruent all the way around. Dropping this part here, remember this is called your apothem because it's from the central angle to the opposite side and it's perpendicular, so we drop an apothem. What that does to the side is it cuts it in half. So with the 7.05 is cut in half. Okay. Once we have that, we have to now calculate and figure out what the apothem is. So you can use a couple different things. If you wanted to, you could find the central angle, cut it in half, and then use trig. Or, in this case, you could use, this is your C, this is your A, or B, depending on how you look at it, and you use Pythagorean theorem. Okay, so let's use Pythagorean theorem. So I got 6 squared equals 3.525 quantity squared plus A squared. So when I calculate this, we got 36 equals 3.525 squared gives us 12.4256. I just want to be as accurate as I possibly can, equals A squared. So I'm going to do 36 minus this, which gives me 23.574375 equals A squared. Don't round until the very end, because the rounding, if you round too early, is going to mess up with the final answer, and you'll probably be a couple units off. Okay, so with this, we have taking the square root of that, so it's square root. So your apothem is 4.855 approximately. Okay, so now this is where it gets a little bit harder. So you have to kind of be able to break down each one of these and figure out the areas of the whole thing. There is a formula that is associated with this, but it's a lot more complicated. So what I'm going to say is I have a top and bottom. That's equal to 1/2 your apothem, which I just found out to be 4.855, times the number of sides, which is 5, times the side length, which is 7.05. Now, I have to multiply this by 2. Why do I have to multiply it by 2? Because I'm doing the top and the bottom. So this is one that I would multiply by 2. Okay, when I get it. So when you plug it into a calculator, you do 1/2 times 4.855 times 5 times 7.05. That equals, and that'd be units squared, so feet squared. Okay, now that's just the top and the bottom. Now we have to do all of the side lengths. But the nice thing is that all the side lengths, the lateral faces, are basically identical. Not basically identical, they are identical. So I'm going to just highlight one of the lateral faces just so you can recognize what I'm calculating. So this is one of the lateral faces here. It's a rectangle. And I do the length times the width, or the base times the height. So the base in this case, it doesn't matter what you call the base, but I'm going to call the base 7. So 7.05 times your height, your thickness, which is 9. And I have to multiply this by 5. Why am I multiplying this by 5? Well, there are 5 lateral faces. There's 1 here, there's 2 here, there's 3 here, there's 4 here, there's 5 here. So I have to account for every single one of those lateral faces. So I will do 5 times 7.05 times 9. So that gives me 317.25 feet squared. Now this is the lateral area, LA. Okay, this is top and bottom area. So to get the total surface area, I have to add these two together. So just so you can actually decipher it between all this. Okay, so for the total surface area, I have to do 317.25, which is the lateral area, plus the top and the bottom, which is 171.13875. If I were to add those two, I get 488.39 feet squared. So that means if I were to put this entire pentagonal prism as a two-dimensional surface, as a net, that means it would cover 488.39 square feet. And if I were to cover that with material, that's how much material I would need. Okay, so the next formula is finding the height of a cylinder. So you are wrapping a stack of 20 compact discs using a shrink wrap. Each disc is cylindrical with a height of 1.2 millimeters and a radius of 60 millimeters. What is the minimum amount of shrink wrap needed to cover the stack of 20 discs? Okay, so first things first, here's the solution. We have the 20 discs are stacked, so the height of the stack will be 20 times the 1.2, which gives you 24 millimeters. So the radius is 60 millimeters, that is what I tell you. The minimum amount of shrink wrap needed will be equal to the surface area of the stack of discs. So you need to know what the surface area of a cylinder is. Here's your surface area formula for a cylinder. The kind of nice thing about a cylinder is you don't have as much work to do as with the previous one, like a pentagonal prism. This is just straight plug and chug. We know our radius is equal to 60. We know our height, our little h, is going to be equal to the 24. And those are millimeters. So all I do is I plug in, I say, okay, we have 2 times pi, and I would use the pi button, or 3.14, unless it specifies. So we have the radius, which we know is 60, quantity squared, plus 2 pi r, which is 60, times h, which is 24. When you calculate that out, you get 31,667.25 millimeters squared of shrink wrap. Now, some people are probably wondering where this is actually derived from. The reason is because here, these are your two circles, your top and your bottom. Okay, so that accounts for the top and the bottom, the top and bottom. This guy right here, if you actually unfolded this part, you would actually get a rectangle. A rectangle with the height of 24, and the length here would be the circumference of a circle, 2 pi r. So you're basically taking the top and bottom, which is pi r squared and pi r squared. So you combine them, you make 2 pi r squared. And then you have this formula right here, which is the 2 pi r, the length, times the width, which is 24. So you're basically using that, so you combine the two to follow or find the total surface area, which in this case is 31,667.25 millimeters squared. Okay, so now that we know the formulas, it says find the height of the right cylinder shown. So, again, all I have to do is I have to know my formula, which in this case is, they tell us that the surface area is 157.08. That equals 2 pi times the radius, which we know is 2.5 from the figure, squared, plus 2 pi r, which we know again is 2.5, h, which we don't know. So we're basically solving this formula. So what I'm going to do is I'm going to do 157. I'm going to use the pi button, so we have 2 pi times 2.5 squared. So we have 157.08 equals 39.2699 plus 2 pi times 2.5. We can't times it by h, so we just keep it as 15.70796 times h. I'm going to do 157.08, and I'm going to subtract the 39.2699. That gives me 117.8101. That equals the 15.07970796 h. So it's basically a complicated, with decimals, algebraic problem. I subtracted the 39.2699 from both sides, and then I'm going to divide both sides by the 15.70796. And when you do that, you get roughly about 7.5 meters is your radius, or I'm sorry, is your height. That's it. So, as you can probably see, the calculations for surface area can get quite complicated very quickly. So you need to know the formulas from previous modules along with the formulas in this module as well.